So I guess we stopped at a pretty good location. So we've done a bunch of commonly used variance reduction techniques. There might be more, but this is quite a bit, covers a lot. So antithetic variates, starting from really simple, Latin hypercube sampling, quasi, and its randomized version. So these change the way we sample, especially these four here, right? How we generate these points. So you just give me the xi or its distribution, right? I'm gonna generate antithetic or Latin hypercube or some kind of quasi-Monte Carlo sequence and then shift it randomly. Important sampling uses the distribution as well as exploit the structure of the problem typically. These ones, as I said, because they only work on the xi, just how you sample, might actually be a little bit easier to deal with, right? Versus this one, there might be some dependence on the x, the solution that you use. The same here for the control variates, right? Typically, so there are cases where people have come up with a general importance sampling, at least for a region, part of the feasible region or an outer approximation of it. But these can be difficult for optimization. So just to give you a recap. Other things, right? So among these, let's say antithetic variates, negative correlation, Latin hypercube correlation because it loses independence. Control variates induces correlations, right? So these three methods will give you correlated stuff, and that's how it reduces the variability. Some of these, right, quasi-Monte Carlo, randomized quasi-Monte Carlo, fill the space better so that you estimate the expectation significantly, with less variance. To a lesser extent, antithetic variates and Latin hypercube also does this, right? It fills the space a little differently than the uniform. So these things have some commonalities, essentially. All right. So is it just another reminder? Be careful with some of these methods, like antithetic variates. For some problems, it can actually increase. If it works, you can combine it with other things. Randomized quasi-Monte Carlo, my experience, high dimensions, really bad. If the problem has an effective dimension, it can still work very well, and so try to determine that. Importance sampling, again, if not selected properly, it can backfire, depending on what you're doing. And then, but if you use them well, you can significantly improve your estimators. You can significantly improve your algorithms, like the one I told you about, this control variates where we partition. Huge amounts of variance reduction. It makes a big difference. All right, so I've alluded at the end of each section a little bit, when used in optimization or someone has done that, here's some, general consensus about these methods. But let's go back when you had the first couple of sessions. You talked about properties of sample average approximation estimators, right? So that all assumes IID sampling, crude Monte Carlo. What happens when we do with variance reduction? Right, so I just want to give you a broad overview of what's happening here. So number one, we had this result. We create an optimization bias. So remember, this is the optimal value of the sample average approximation problem. It's trying to estimate the true optimal value, but think of it this way. You have a whole bunch of variability, but you sample some of them, so you over-optimize for those things. So if you're minimizing, you're over-minimizing, which creates a bias, all right? So this type of bias is actually more general, so you can, than IID. So if you have a sampling scheme that basically gives you unbiased estimators, all right, then you still will get the same optimization bias. Will still be present, okay? Theoretically. And when do we see unbiased estimators? Pretty much all of the ones that we covered, because we wanted unbiased but lower variability. So for example, antithetic variates, but you have to make some adjustments there, right? So antithetic variates, unbiasedness will be equal to, the estimator will be not that, but 1 over n over 2, the g of x cj plus g of x, the antithetic variate, divided by 2. j equals 1 to n over 2. So instead of this thing, this estimator is unbiased. Right? So I mean, if you just do some adjustments on the this quantity here, you have very easy unbiased estimators, Latin hypercube sampling, obviously unbiased, randomized quasi-Monte Carlo, unbiased, important sampling, unbiased, even if you choose the bad distribution. Control variates, if you use lambda, that scalar that you add the control variable. If that's a scalar, you can use 1, for example. Or if you know the covariance and the variance, you can use the optimal one. If you use a scalar, then it will be unbiased. So many of these things will actually work. One thing is that from the literature, right, so antithetic variance, Latin hypercube, randomized quasi-Monte Carlo, they actually reduce this bias. Even though it says I'm still going to have some optimization bias, but because they sample kind of better than the random, they actually like give you a better estimate of what the optimal value should be. So you get a side benefit out of them. Okay, it might be possible others do that, but that's the idea. Okay, so in optimization, you gain actually from better sampling. Typically, bias reduction comes as well. All right. Next thing, we can ask questions. So that thing is quite general. We had it for crude Monte Carlo. We have it for these bias reduction, variance reduction techniques. What happens to the consistency or strong consistency of the optimal values and the optimal solutions, right? So you must have seen in Tito's lectures, under certain conditions, the optimal value of the SAA problem will converge to the true optimal value with probability 1. And the same thing for the solution, and this is written with respect to solution sets. So there might be multiple optimal solutions here, multiple optimal solutions there. The distance between these two sets goes to 0 with probability 1. So eventually your SAA will give you the true problem solution and value. So what happens when we go from crude Monte Carlo to one of these variance reduction schemes? All right, so AV is always easy to deal with. Why? Once you do the pairs, and once you rewrite your, so basically you change your random variables to this plus the antithetic variate divided by 2, then you create each one of these j's, n over 2 pairs are independent, identically distributed, each pair. Okay? So you revert back to IID sampling. You just have to be, change your variance term. So instead of the variance of the G, maybe you want to look at variance of this thing, which will be actually less than that. Just the variance of the G's, not divided by n. Anyway, so once you do those modifications, it's back to the IID case. So everything pretty much works. So theoretically, it's very easy. Latin hypercube, somewhat similar. Might require some additional conditions, slightly more conditions in some cases. So for example, so one of the ways, especially this one, to show this, you need uniform strong law of large numbers, right, instead of the strong law of large numbers. If you have uniform strong law of large numbers, then this will follow. And how do you get uniform strong law of large numbers? One way to think about it is if you have pointwise to begin with, you might want to have pointwise strong law of large numbers. By the way, everybody knows what I'm talking about. Okay, some people do know very well, some people not so much. Just to make things a little bit more concrete, right? Strong law of large numbers in my context basically says if I have a sample mean, so let's do R estimator for a fixed x. Okay? And I look at its estimate. This g of x is the expected value of this capital G. Right? This is what I'm trying to estimate. If I can write this. Okay? So I look at that, right? As the sample size increases, this goes to 0 with probability 1. as n goes to infinity, strong law of large numbers, sample means converge to the expected values, IID sampling, assuming in the IID case, you need to have, obviously, well-defined and finite expectations. So you need the first absolute moment to be finite, okay? So under this condition, you're going to get something like this for IID sampling. This is for a fixed x. All right? If you do IID, you have this condition satisfied for all x in your feasible region, all right? But that's not enough to guarantee this. You need a uniform strong law of large numbers. Uniform means, right? I mean, we all know I take the soup, and this still goes to 0. So if I get that, then I'll have this. Under some additional conditions, I'm going to get that as well. So say continuity and stuff like that, compactness and whatnot. So again, one way to show uniform is you have pointwise, and then if it's convex, continuous, etc., then you automatically, or x is finite, for example, you automatically get uniform convergence, right? So these are easy cases. But if you look at, for instance, the strong law of large numbers, instead of this, you know, I need the square of this to be finite. So it's a little bit higher moment condition here. You know, for example, central limit theorem for Latin hypercube requires boundedness. Versus in the regular IID case, you need, say, second moments to be finite. So it requires just a little bit more under certain conditions. And people have looked at, including my student here, Tito's student, it will satisfy these things. Okay, not so difficult. All right. When you go to randomized quasi-Monte Carlo, people have used, so epiconvergence is one way of dealing with optimization problems and their convergence. One thing is definitely needed, the star discrepancy to go to 0. Well, in the randomized case, it should happen with probability 1 as n goes to infinity, right? At least you should have that, because otherwise you won't have convergence. So this way, this will sort of mimic a uniform distribution. And then once you do that, then you can show certain conditions and compactness and whatnot. You'll get these results. Okay? Similar things with quasi-Monte Carlo. Even though this is a deterministic sequence, but it will still converge to, like, it will fill up the whole space. So you can do a similar thing. So it will be deterministic. So this should have with probability 1. This doesn't have any probability in it. Okay, something similar. So I'm skipping a bunch of conditions on the G and the X or something. But, all right. How about rates of convergence? Okay. So with Tito, you must have looked at 2 types of rates, meaning the rates of the optimal values, right? So this is kind of like you can do sort of central limit theorem type of result for the optimal value, right? And then you can also look at the solutions, optimal solutions as well. So this is an assumption. So piecewise linear or finite. So either my problem has this kind of a structure, so X is convex and compact. G is convex and piecewise linear on X. And then C has finite support. Or I just have this finiteness. As I said, these all help with this strong, uniform law of large numbers. So again, as X is finite, I'm going to have that automatically, right? I have a finite number of points. Kind of done. Each one of them satisfies, so I'm done. And then here, yeah, convex and continuity, convexity always helps, right? So under these conditions, you have nicely behaved problems. So for these problems, which would be like 2-stage stochastic linear program with finite support and maybe some integrality, integer program in the first stage. So if this assumption holds, the true problem, and suppose, for simplicity again, you have a unique optimal solution. Okay? And this is going to look familiar. And suppose the central limit theorem holds pointwise. So for each x, okay? For each x, I can write my estimator minus the mean, the thing that I'm trying to estimate, divided by the variance of my estimator, which is here, will converge in distribution to a standard normal, all right? This holds for each x, especially I'm writing it at the optimal, the unique optimal solution, okay? So does this hold for IID sampling, crude Monte Carlo? Central limit theorem, normal. Yeah, I mean, if I have finite this variance, then it's going to hold, okay? For non-independent ones, there are some additional conditions. So for example, like antithetic variance, again, you just change your definition here a little bit. Oh, I erased it to the sum divided by 2, change your variance definition a little bit, and it's good to go because it's like IID, okay, assuming finite variances and stuff. And then, you know, when you have Latin hypercube sampling, again, the conditions are a little bit more and so on and so forth, okay? But you can have this. This is easy because it's at each x. So it's like you're doing regular statistics. When you optimize, then you need uniform version, okay? Anyway, so it's possible to show for those problems, for those types of problems, then you can show the optimal values also satisfy some kind of a central limit theorem, okay? Do you remember what Do you remember what happens if I don't have a unique optimal solution here? So if I have a unique optimal solution, this is great. It goes to a standard normal with this variability given by the variance of my estimator, which in the IID case, it's the variance of the G divided by capital N, right? But in, say, Latin hypercube, it might be different. What happens if I don't have unique optimal solution? Do you remember? Want to speak up, maybe? No? Okay, it's fine, it's fine. So we remember, that's good news. It's basically going to be like a infimum of a bunch of normals. I mean, you can take this on the other side, and there's going to be some rate of convergence here, by the way. So rate of convergence will be square root, or 1 over square root of n. So variance divided, you know, square root of that is going to have 1 over square root of n here. But for the IID case, for other cases, it might be different. Depends on the sampling. But let's say the IID case, so square root of n, I move the variance over there. It's going to be a minimum of, say, a bunch of normals. So it's no longer normal. And I think there's a negative in there or something, right? So not normal, but it still has some kind of a convergence. And it's over the infimum of all the optimal solutions of the set of optimal solutions. Okay? Anyway, so standard Monte Carlo, we have seen, as I just told you, square root of 1 over square root of n. And so AV, with some changes, same kind of order of convergence here, rate of convergence on the optimal values. So Latin hypercube, I've already told this, so for a pointwise central limit theorem to hold, I need bounded functions. And that's all, both in X and C, I need some boundedness. And if it's not additive, so additive means ANOVA decomposition of functions. So I take a function, it's like C, has like 10 dimensions. I basically, if I can write it as a part that only is like from the first dimension plus the second dimension plus the third dimension plus, you know, up to 10th dimension. And there's no residual term. So this is kind of separable function, all right? The ANOVA decomposition won't have any residuals and whatnot. So if it's additive, actually, this is 0. So it gets a little bit tricky, right? So there's no, you know, the variance goes away because you use all the dimensions kind of thing. But if it's not additive, then you're going to have the finite variance in there. And then the rate of convergence is still going to be like the standard Monte Carlo. So the rate of convergence didn't change, actually. But it actually behaves better. Right? It has lower variance. It actually also reduces bias for this expected value problems. All right. So randomized quasi-Monte Carlo is a little different. And so central limit theorem for or randomized quasi-Monte Carlo is hard to come by. So there are some, let's say, some versions that have this. And for that version, you can show some properties of this variance. Sorry. the variance that shows up here, right? It's no longer like this, square root of that variance divided by n. So no longer 1 over square root of n, but it's going to be log n dimension minus 1, n cubed, and the square root of that. Okay, again, asymptotically better than the standard Monte Carlo, but depending on the dimension, it can be better, or depending on the problem type, right? So some problems with the lower effective dimension actually goes down really, really fast than what this says, okay? But for some other problems, it can, as I said, can be quite high for high dimensions. So those are the rates of convergence, okay? So the analysis is a little bit harder than IID, but under certain conditions, you can still recover same type of results, possibly with more stringent conditions attached, all right? So how about optimal solutions, all right? Again, so just again for simplicity, you can show things like this, weaker conditions, but under weaker assumptions. So piecewise linear or finite x holds. Then, if the exponential rate of convergence holds pointwise, right? This is like if you have large deviations type of results, you can get these constants that will depend on x, by the way, right? So this tells us, hey, my estimator, the deviation of my estimator from the thing it's trying to estimate, which is the mean, that deviation to be larger than some delta, okay, is shrinking to 0 exponentially fast. How fast it is, of course, depends on this rate, okay? If this is small or large, well, it will shrink fast, or it might actually be not as fast. And there is a constant here as well. So if this happens pointwise, then you can show similarly for this class of problems, okay, that my sampling optimal solution is not an actual true optimal. The probability of that will go to zero exponentially fast. Or put another way, with probability 1 exponentially fast, I will find an optimal solution, as I increase the sample size. Okay? So these constants, by the way, k and alpha, so here we took out the dependence on the x, but they do depend on how the sampling methods work. So if you can get a faster sort of these probabilities, faster rate of convergence, right? Faster shrinking of the probabilities, then this will also go to 0 faster, okay? So for Latin hypercube sampling, for some types of functions, G is monotone. We've seen this before. So if it's monotone in each component of C, for example, people have, you can show that the large deviations hold pointwise, then you can actually get this for the optimal solutions of the SAA problems formed by Latin hypercube sampling. And the result is that this rate will be at most like a standard Monte Carlo. It's a bound, but in reality, it's actually typically faster. It goes to 0 faster than standard Monte Carlo when you have this property. Okay? So these are how you extend this type of results that you have seen earlier in the SAA. Any questions on these? Okay, so just giving you a broad overview. I guess I have some final remarks. I've said this before, like variance reduction, it can be even more important for optimization, right? You're trying to solve something. You're estimating the gradients, objective function values. If you can do them better, you might perhaps do much better. And you can show asymptotically as the sample size increases, you can get similar results, even like a little bit better rates of convergence and things like that under certain conditions. However, if they're not used properly, some techniques may backfire, so be careful about that. So you put all this effort, you don't want to do worse, right? And then there's still a lot more to do. Especially as I was talking, like this risk-averse optimization is becoming a lot more common, and how to do this sampling in a better way, there's a lot to be done over there. Okay, so if, this is an open area of research, lots of good things to do. And some of the references, I know not all of them compiled. I think these are the ones that didn't compile. Anyway, so this is the end of the variance reduction, just giving you a broad overview. Any questions or comments? Okay, it's the end of the day, I guess, huh? You're tired. Let's see. Okay. So I'll start with another recap kind of a thing. Somewhat generic stochastic optimization. So before, mainly, we were concerned in cases where there were no stochastic constraints. So some part of this presentation was to had some stochastic constraints in it, but unfortunately I lost some things. So we'll have only partial, but that's why I had it here. So objective function, right? I'm trying to minimize some expected function. Again, this could be an indicator, so minimize probability. It's a little bit more general. These could be, you've seen chance constraint, value at risk, expected value, conditional value at risk, and so on and so forth, right? So the type of problem will depend on all of these things. The X, how many stochastic constraints I have, what type of constraints I have, and so on and so forth. So again, just a broad overview, like we've seen this before. No stochastic constraints, linear first stage, linear first stage cost, and the objective function, which is convex, of the second stage. And all of these is a linear program. Right? Or chance constraint, if I want to write this chance constraint, minimizing a linear cost, I write my G function like this, my kappa number of stochastic constraints is 1, and so on and so forth. Okay, so 2 types of general problems, for example. So suppose for now, I have no stochastic constraints, just like we did most of the variance reduction stuff. All right. Now I want to talk about solution quality, all right? I have some candidate solution, and I might have obtained it in many other ways, right? So I have done maybe a sample average approximation problem. Maybe I have generated this in crude Monte Carlo, or maybe I have used Latin hypercube sampling and whatnot, okay? So most of the time, the best I can do is get an approximate solution. I cannot solve this thing. And I might do it iteratively in an algorithm, so stochastic decomposition, stochastic approximation, or any other method you want to use. All right? So I have this. Then one way to look at the quality statements we looked at as n goes to infinity, right? Do I have the convergence? Will I converge to that thing? And how fast will I converge, right? I mean, I have the exponential rate of convergence perhaps, but if the rate is small, even though it's exponential, it might go with probability really, really slow. So I want to do this for a finite sample size, okay? I don't want to do it asymptotically for large sample sizes and so on and so forth. And if I use the large deviations theory to come up with the sample size, I have the probabilistic guarantee, that will give me a very conservative result, actually. And it has quantities. It was in the other thing, but there's the Cx, e to the rate n times the rate function. Those quantities are not easy to, you don't know them, you can estimate them, but they're not easy. So if you want to use them, they're more qualitative in nature, not quantitative, okay? So I want to do this for small sample sizes, and I want to do it in an easy way, okay? How do I do that? I can, again, use sampling, actually, to do this. Okay? So that's this talk is going to be about that. So quality of my solution, I'm going to define it as its optimality gap. So this is used a lot in any optimization algorithm, deterministic, stochastic, whatever you're trying to do. So you give me X, a solution, and assume it's feasible, obviously. So optimality gap, I'm going to denote it as mu of x. It's its objective function value subtracted from the best we can get, right? This is the minimal value I'm minimizing. So this quantity is always greater than or equal to 0. The larger it is, the worse the quality. If it's 0, it means it's an optimal solution, okay? So obviously, I want to know what this is, but two problems. So in deterministic optimization, it's the same thing too. I have a deterministic problem, like say mixed integer, semi-definite program, whatnot. I want to calculate something like this. I don't have an expectation typically. I just have a function value. So maybe I can calculate the function value in the deterministic case, but in the stochastic case, I have this expectation. So even for a given x, right, it's a multidimensional integral, for example. It's very difficult to calculate this. So, on the other hand, right, I mean, also, we don't know what the optimal value is. Of course, we cannot calculate this. Not even this term, but definitely not that term. If I knew this, I'm done anyway, okay? So this is the same kind of problem in deterministic optimization. You want to know, like, so you're doing branch and bound. Do we know branch and bound? Some of you, this side a little bit knows, this side not so much. Anyway, so any optimization algorithm will generate a sequence of solutions, and then we'll try to estimate how good it is. And the way they do it is you don't know what the optimal value is, but you find a bound on it. Okay, you say it's this way, but all I can tell you is it's within like a certain number. Okay, and the way to do it is you get relaxations and whatnot. So, so for example, if you're solving integer programs, you relax the integrality if you know this kind of stuff, like in a branch and bound. The linear programming approximation will give you a lower bound on this thing, so you create an upper bound on the optimality gap. For example, you can do better, like you can do Lagrangian relaxations, semi-definite relaxations, and whatnot. So this is fundamental in optimization. If you want to optimize algorithms, you always want to get some kind of an estimate of this because you want to stop when you feel it's close enough. Okay? You have to be able to determine this. All right. So in stochastic programming, you can think of something that we've already seen as another type of a relaxation bound, but it's unique to stochastic optimization. So what is this? I've already shown you just several slides back. If I have sampling that's unbiased, then, here's the proof of it, which is immediate, right? So expectation of the minimum is less than or equal to minimum of these expectations. Then basically I have this optimization bias, right? Okay. So again, you can think of this as a relaxation bound. What are you relaxing? You have your distribution xi, right? You're taking expectation with respect to that. But instead of that, you generate a sample. So you relax the overall thing. So just think about it intuitively that way. So you're over-optimizing over there, and you're getting, on average, something smaller than the true one. Okay? So you created a bound on it. Just like you relax the integrality constraints in integer programming, you get a linear programming relaxation, you get a lower bound on the optimal value. Similar idea, but statistical bound, right? On expectation, it's lower. All right. Which is what we have. Biased estimator, if in statistics. In optimization, right? Oh, another result here. If I have IID, so crude Monte Carlo sampling, for the other ones you need perhaps some conditions. But definitely for IID sampling, you can show that this bias will shrink as you increase the sample size. And we already know we have the with probability 1 convergence and the convergence rates and whatnot, right? And this shows on average it's going to, on expectation, doing the same thing. All right. Bias shrinks. That's a statistical estimation. So we're going to use this bound, just like they do in deterministic optimization, to create a solution quality statement. Okay? And it's very simple. So if this is my optimality gap, how far my objective function value at x is from the best I can do, then I can easily bound this in expectation, right? Like using this quantity because this is because of the relation between these two things. So I created a bound on it. All right. And once I do this bound, again, I cannot calculate this even for a given x. Obviously, this is harder, because then you have to generate all sorts of n samples and optimize them and get the optimal value, take its expectation. Much more difficult. But, so this is an expectation of this minus that. So I'm going to create an estimate of this expectation by regular sample mean. Right? I use regular statistics. On this one, I'm just going to use, typically you can do it different ways, but let's assume I use the same samples and I optimize it in my feasible region. And this is what I call the sample average approximation optimal value. Okay? So expectation of this is exactly that, which will give me a bound on this. Okay? So I have a kind of an optimality gap estimate. On average, it's going to give me a bound. Of course, it can go up and down. Okay? Now, what are the properties of this thing? So if I do, say, crude Monte Carlo, right? This is an unbiased estimator of that. It will converge to that by strong law of large numbers, and so on and so forth. This one is an optimized, so I know the bias exists. Also, unless I have unique optimality and, you know, this some Lipschitz and so on and so forth condition, I might not have asymptotic normal distribution of this guy, right? So there are only like certain conditions that you've seen in the earlier lectures that it might be asymptotically normal. Also checking if it has unique optimal solution is, how do you know, for a given problem? You cannot solve it, right? So this is not going to be asymptotically normal, so it's not that easy to deal with. So what do we do if we don't know what the distribution, even asymptotically, we don't know what it is? We've used it before in the randomized quasi-Monte Carlo. We take replications of this and use approximate central limit theory on those many replications of this. Okay, so that's called a multiple replication procedure. So what does it do? You give me a solution. All right, X. And I want a point estimator on its optimality gap. And that's not enough, typically. I want a confidence interval that's, say, 95% level, and using sample size, say, n, and a replication size, ng. And I'm going to give you a point estimate and an approximate confidence interval on the optimality gap. Okay? So I take ng replications. So if you, in classical statistics, what's the rule of thumb? 30, 25, something. You need to have at least that many observations, to get to some kind of an approximate normality. So you can do something similar there. 25, 30 replications. You sample IID observations. Again, you can change this to variance reduction techniques. And then solve the sample average approximation problem. And then this will give you basically one estimate of this. Okay? And then you're going to do it m times, or ng times. Once you do it ng times, then you average them. So that's your sample mean, and that's your estimate of the optimality gap, point estimate. If you want to create variability, or you want to know how good that estimator is, you create a variance on it using the replications. So 30, 25 of them. Same old sample variance estimator. Each individual observation minus the mean, squared divided by 1 over number of replications minus 1. And then, even though this is not asymptotic, this guy, we don't know if it's asymptotically normal or whatever it is, right? Once we do this, no matter what these distributions are, as long as these replications are generated in an IID fashion, I can use central limit theorem type of result. Because I'm going to treat each one of these, or each one of these, each gap estimator, whatever its distribution, I have no idea. But I can use approximate central limit theorem, and then, there's some typo there. And then I create a confidence interval. This is the sampling error. So t distribution quantile, and then the variance standard deviation estimator divided by square root of ng. All right. I think I've talked about this. So this will be asymptotically valid when these batches that we create are independent identically distributed. So be careful. It's the batches that are identically distributed. So within each batch, I can use variance reduction easily. I can do this AV, I can do randomized quasi-Monte Carlo, Latin hypercube, as long as I create the next batch independently and in the same way as the first batch, and the second way, and for each one of them. But as long as the batches are IID, I'm good to go because I can use central limit theorem on the IID gap estimators. And I must have finite second moments at least because I have the variance to use central limit theorem. And then I need consistency of the variance estimator. And typically you might need a little bit more than that, but it's still fine when you for these things. Once you have that, then you have the central limit theorem and the consistency of this estimator to the variance of this. And again, under IID batches, you should get this, right? And with the second, maybe fourth moment or something. So a little bit higher moments, you should get this. Then you can write the central limit theorem. It will converge to a normal, blah, blah, blah. Regular old statistics. So what does it mean in the end? So when I write that confidence interval here, okay, and you can replace this assuming a large enough sample size or a little bit conservative with the T quantile. There's a typo here, by the way. This shouldn't be here. All it's saying to me is, look, this is my expected g of x. This is what I'm trying to, remember, this is what I'm trying to estimate. This is the optimality gap of x, okay? It tells me my optimality gap for a given solution x is within the width of my confidence interval, approximately 95% probability, okay? So this is actually limiting because of the CLT, central limit theorem is a limit. But what happens when you do this, this is actually a lot more conservative. So you want 90% or 95% confidence. It will give you 99. Okay? And why is that happening? For a, I know as this goes to, as the number of replications goes to infinity, this will be 95 or something. But, normal statistics, it will be less than that typically. In this case, it's a little bit more in practice. What's happening? Any guesses? Too tired? Too much talk? Too many slides? All right, let's take a look at this. So I have G, like my optimality gap estimator, and then at central limit theorem, I subtract its mean. So do you remember what's the mean of my optimality gap estimator? Is it this? Is it the optimality gap? No, it's not. Where is it? This is my, say, optimality gap estimator, right? Its mean is this quantity. It is not that quantity, okay? So it's something higher. So it's more conservative, right? Because it's creating an upper bound on average on the true optimality gap because of the optimality bias, okay? Because on average, this is lower than the true optimal value. So that's why, if you have smaller sample sizes, it will overestimate the optimality gap. It will tell you, oh, it's like this. In reality, it should be much smaller, okay? So it depends how much bias your problem has. Some problems have very little bias, so you don't have this problem. Some problems have a lot of bias, so you have this issue. But that's why, in the context of the stochastic optimization, right, unlike maybe regular statistics, this will give you actually more conservative results. All right. So advantages of this procedure, it's widely applicable. So in here, when you study these rates of convergence, the central limit theorem type of result, there are all these assumptions, this should be convex, compact, and this should be continuous, all of that stuff, or Lipschitz continuous, and so on and so. Here, I don't need any of those stuff. This can be convex, it can be non-convex, it can have integrality restrictions or not. This guy can be convex, smooth, or not, right? As long as I can generate these optimality gap estimates, and I have sort of finite some moments, then I can apply this because I'm taking replications, no matter what the distribution is, no matter what these functions are, then I should be able to come up with these optimality gap estimates. In fact, people have used this type of results, this replication idea on, say, chance constraints or some other types of like probabilistic constraints. It's a very common method. So another advantage is that it's because you're using Monte Carlo, you can adapt any algorithm for your problem, right? Because I create a sampling estimate, I optimize it. Depending on my problem, I can use like a really fast algorithm. So it doesn't specify what you need to use. But I mean, some disadvantages. So one of them is, look, you give me one solution, and I've actually spent a lot of computational effort to get that probably, right? I have done my algorithm, I have done this, I have done that, my sampling generation, and so on and so forth. And then I give you a solution, and you have to generate, say, 25, 30 problems, 30 optimality gap estimates to come up with confidence interval, right? And by the way, each one of these replications, you need to solve a sample average approximation problem. Why? It's by the definition, right? One gap estimator is like a regular sample, that should be G, regular sample estimator, plus, I optimize this, okay? All right. So I need to solve SAA for each one of these. So of course, why do I need to solve 30 of them, right? That's one computational burden. And then, as I've already discussed, it can overestimate the true optimality gap because of the bias. For some problems, this could be an issue. So if this estimator is large, right, first of all, bias can be large. Just we talked. If the bias is large, it's going to tell me, hey, optimality gap is this versus it's actually much lower. Or you might have a lot of sampling error. Do we know what to do in that case? I think so. I hope so. And the third problem is, even if bias is low or sampling error is small, you might have a truly bad solution. So, but you don't know what it is, right? So you want to get a better optimality gap estimator because you don't know if your estimate is bad or if the solution is actually bad, okay? And there are some remedies to deal with these. So first of all, the first issue is like this, why do I need to solve 25, 30 problems? I can actually do a single replication, calculate only one, and I can get a confidence interval, okay? So you only need to solve one optimization problem. So this is what we call a single replication procedure. And you can do two, which is in practice better. Another thing is when the bias is large, right? This will cause issues. So you can employ bias reduction or variance reduction techniques. As I discussed before, variance reduction sometimes decreases the bias, so you get this, you can do this better. So I've worked on some remedies for that. So when the variability is large, it's easy to do variance reduction each batch, as long as they're IID. You can also do this for the single replication procedure, by the way. The other thing is when the candidate solution is far from the optimal, you don't know, so you can embed it in your optimization algorithm. So you generate a sequence of solutions, and you stop when you believe it's, the optimality gap is small enough. Okay, so you need to change the sample size, increase it, and then you need to change your candidate solution and stop at a high-quality solution. So these are called sequential sampling procedures. Okay, so you can do a number of different things. Any questions so far? All right. Yes, absolutely. I will talk about it. But I have to revert to the board. As I mentioned earlier, I had some issues with my slides. Okay, so single replication procedure. So let's call it SRP. So what's our gap estimator, right? I have this, I wrote it as a calligraphic G of n, let's say, of x. I create a sample. So far, let's use crude Monte Carlo, the regular Monte Carlo. I look at these estimates. Let's use the J here. Okay, so this is my sample mean. This is going to estimate on average, right, this quantity. And then I subtract its minimized version. Okay. And this is what we call nu n. And on average, it's going to be less than the true optimal value. Okay. Now, as I said, I don't know in general what this distribution is going to be because of this minimization. So the single replication, do only one. So let's rewrite this quantity, okay? When I minimize this, what is an optimal solution? How do I denote it? There might be multiple, but let's use one optimal solution. So you put it in your optimization, GAMS or whatever, Cplex. It gave you a solution. What do we call it in our notation? Xn star, right? So I'm going to replace this by basically writing this. J equals 1 to n. G of, instead of the minimization and the x, I'm just going to replace it by Xn star. Okay? That's it. So I took out the minimization, but I put in the optimal value directly. All right? And the first term is exactly the same. Okay? Again, I can rewrite this as like this. All right? So I take my candidate solution x. I look at it across all samples j. And I subtract g of xn star cj. Right? This is exactly the same thing, which is exactly this. Okay, I'm rewriting the same thing. Now, can you see something here? What is this looking like? It's looking like a regular old expectation, right? Where I have each individual observation is this difference. Are you with me? Okay. So let me ask you a question. So for each j, 1 to n, are these differences independent? So I do crude Monte Carlo. I do IID sampling. So each Cj here is independent. Okay, so let me ask you, each one of these quantities, are they independent? Yes. How about these differences? No, they're not. Why? I'm assuming here I'm using the same sample that I have calculated this, and I minimize the same sample, average. Okay? Which means this Xn star depends on all of the CJs, right? So you give me a sample, n samples. I optimize it. That will obviously depend on the sample I generated. So each one of them will have this. So this difference random variables are no longer independent from one another. So the statistical analysis of this is a little bit harder, but you can show that you can view this, just these difference random variables, as like kind of like regular old, samples, and then use only one optimality gap estimator. But you need also a sample variance estimator. So how do we generate a sample variance estimator? Assume they're independent. This is the mean. What do? Individual observation minus the mean squared divide by total number of observations minus 1. Okay? So let me write it here. S G, let's call it, of x squared. Can you see this when I write in this guy? With this color? Okay? So I'm going to just treat them as regular old random variables to, what do I do? This is a sample mean. I do n minus 1. Okay? And then I do, for each observation, and I have n of them, I take the individual observations. I'm running a little out of space here, but xij minus g of xn star xij. And I subtract the mean, which is my one optimality gap estimator. Okay? And I square those terms. All right? Looks like a regular old sample variance estimator, but it's not. And it's the same fact that these are not independent anymore. Yet again, you can show certain properties of this. All right? You can show something like this. May I erase parts of this? It's going to be difficult, but all right, let me do this. So for simplicity, let's say unique optimal solution. And let's call it x star. All right? So if I have x star that's unique optimal, and under certain conditions, right, I know something like this. This xn star, or whatever we called it, is going to converge to x star with probability 1. Right? Because I have unique optimal. Suppose the sample problems also have unique optimal solutions. Otherwise, you can write it with that distance of the optimal set, things like that. So we're going to have this convergence. So when you look at this, so let's create a variance. So let's call it sigma squared x, okay? And that's going to be the variance of this kind of a difference, except that x is given. This is my candidate solution that I'm trying to estimate its optimality gap. Minus, this is a random quantity, right? It's a random vector of decisions. It's the optimal solution of the SAA problem. Instead of that, I'm going to use a true optimal, which is a fixed quantity. If I knew it, it's a fixed number, or a fixed vector, right? G of, because it's a unique optimal, G of x star xc. Okay? So I look at the variance of these different random variables. All right. Now, I can show that under, say, continuity, X compact, and things like that, where you will have this, as well as because of the continuous of the G function, right? If it's continuous in X, as Xn converges, G of Xn star will also converge to G of X star, right? Because of continuity, definition of continuity. So under certain conditions, you can show that this estimator will converge to that with probability 1. Even though you don't have independence anymore, okay? It's possible to show this will converge to that with probability 1, okay? So now, once you have this, together with the optimal values converge and whatnot. Because the optimal values converge, each gap estimator, G of nx, remember, this is a regular sample mean, which I know converges for sure to the expected value under IID sampling, or other samplings too, for most of them, minus, so remember there is the nu n there, so under conditions where also the nu n converges to nu star with probability 1, the single optimality gap estimator will converge to the true optimality gap with probability 1. okay? Even though I have dependent components in each one of them, I can still show some kind of properties, okay? Once I have those, then I can use sort of a tilted center limit theorem, because these are more conservative than a normal, typically if you have multiple optimal solutions and whatnot. So it's possible to show this. My point estimator is just one single gap estimator. My confidence interval estimator is given by this. 0, because it can never get, it's one-sided, it can never get below 0. If it's 0, it's optimal. And then I do point estimate, just one of them, plus, let's say we have sufficiently large sample size so I can use the normal quantile. You can also do T quantile, although it's not theoretically T distribution. But in the limit, it's fine either way. You can use Z. Then this S estimator, the square root of this sample variance estimator, SG, divided by, you've only used 1, so it's going to be square root of n. Okay? As if you had independent samples, but you do these, you look at these differences. Okay? So if you write this, you can show a similar result. So this is the single replication procedure. You can show in the limit the optimality gap, the probability that the optimality gap will be within, not the multiple replication procedure, but this confidence interval, okay, is the worst limit, lim-inf, is going to be greater than or equal to your desired confidence, say 90, 95%. Okay, so you can still show, even though it's not asymptotically normal, or you don't know if it's asymptotically normal or not, you can still show this works. It's asymptotically valid confidence interval. So what is the difference between, say, the multiple replication procedure and the single replication procedure? Multiple replications, you have, obviously, a bunch of these G estimators, the gap estimators, right? 25, 30 of them. And how do you calculate the variance? This quantity. You look at the variability of those 30 estimators, okay? The main difference here, or two main differences, in the single replication procedure, you have only one point estimator, okay? So how do you calculate this variance? It's the way I showed you. You look at the differences and treat them as individual observations, and you calculate the sample variance that way. So the sample variance is the main difference between them. Okay? I have only one observation here, so what's the variance of a one observation? There's no, you cannot calculate. You have 1 over 1 minus 1, 1 over 0, undefined, right? So you basically look at the inner part, and in each one of them you have n observations, so you take the sample variance of those. Okay? And so you can still do this. All right. So what are the good things about this? What are the bad things about this? Okay, good thing is, I had 30, optimization problems to solve. Now, I got rid of that problem. I only estimate one optimality gap, and I'm kind of done, right? And I can estimate the variance once I estimate that. So computational burden went down. Is it better? It's less conservative, usually. So much so that it actually underestimates. So this multiple replication overestimates because of the bias issue. This one has a bit of a degeneracy issue, meaning if you obtain your candidate solution from, say, sampling, and then to calculate the gap estimate, remember, you solve a sample average approximation. Suppose the two are equal. What is going to tell you? The gap is 0. Because you obtain the same solution. So it can come out with degenerate sort of like 0 gap, 0 variance. All all right? And this can happen, which will actually lower the coverage of these single replication procedure. So it has that danger, okay? When you do multiple replications, what do? You create more variety, so you get a better estimate in some sense. When you do single, you have only one thing, so if something goes wrong, right, you just give incorrect results. So that's the negative part of it. So we came up with a compromise, which is the 2 replication procedure. So instead of doing 30, you do 2 of the single replication ones, all right? And the main difference is you take a sample size, let's say n, and then another n, or just n divided into 2. You generate one single gap estimator. Okay. So that's going to be 2 replication or average 2 replication procedure. You have sort of 2 independent samples. Let's say n and n, or you can do n over 2, n over 2. You generate one gap estimate here. Independently of the first one, you generate a second gap estimator. And for the first sample, you generate, let's call it 1. Let's call it 2. You generate this, what did I write it? Like that, I guess. This different sample variance estimator for the first sample. You do the same thing, but you do the single replication version of the sample variance. Okay. Now, in statistics, you can pool things and you average them. They actually give you a little bit better things because you reduce the probability of that degeneracy issue happening, okay, when you do 2. But you don't want to do too much, because then your computational burden will increase. So what is your estimator? 2 independent samples, same sample size, 1/2, 1/2. What is your variance estimator? 2 independent samples, so kind of a pooled, sample variance estimator. You take the average, and this is your gap of the average 2 replication procedure, say. That's what you use here. And then, and this is the same sample as A2RP of X. And then you can basically do something similar over there. So you combine the 2 of them, and it will give you a better estimator. Let me see if I have earlier. See if I can have. So I don't know if you can see this. This is not a Newswander problem, but the top one is the multiple replication procedure. As I told you, it overestimates. So it uses a sample size of 100 for each one of these things. And then it generates 30 of them and takes the average and then calculates the thing. So this is the coverage probability, by the way. We want 90%. So we know in the limit it will go there. Okay? But it goes from the top. So it overestimates, especially smaller sample size means higher bias. Bias shrinks as you increase the sample size, which means multiple replication procedure will go to 90% confidence from above. So if you want to be conservative, go ahead and use that, okay? That's important to you. The single replication procedure is this blue one. It's from the bottom, okay? So it's underestimating because of this degeneracy issue. And so it's, again, in the limit, the theory says it will go to at least 90%, and it's doing that, but it's going from below, okay? And then when you do the 2 replication procedure, I think that's the green one over here, So it kind of flips around the single replication, and it's not as high as the multiple, but it's definitely low, not low like the single replication procedure. It can be a little bit problem dependent, but this kind of hedges against, things going a little bit wrong in case something goes wrong, okay? And so you can do that. And the other ones are sort of test things. This one uses, what is this? Gap estimator from one sample, so it doesn't average. So it uses independent gap estimator, independent sample variance estimator. By the way, the problem arises because in the single replication, the gap and the variance are dependent on one another. Remember, they all use this xn star and the optimal solution, so there's dependencies between them. So if the gap is low, the sample variance will be low because you're using those individual estimators. So that correlation kind of makes things a little bit bad. So this independent to replication, right, it increased the probability, still going up. But, you've already generated 2 samples. Just use both of them and get something a little lower because you want 90% confidence. And then the true uses the true variance estimator. Okay? So that's the single replication procedure, but I do recommend doing the 2 replication procedure. Okay? So we have done this for, say, 2-stage problems, but there are kind of versions that can be done on the multi-stage trees as well. All right? It's a little bit more complicated, but it can be done. Any questions on the single replication one? I think it's square root of 2n, right? I think it's square root of n. Let me check just to be on the safe side. Let's see. Yes, it's square root of 2n. If I do n and n, yes, it should be. If I do n over 2, n over 2, then it should be, total sample size. Thank you. Yeah. It makes sense. But, so be careful about that. Any other questions? All right. So we have what time? 5? That's what's going to end. Okay, so maybe I can also talk about how to use this in a sequential fashion. Okay, which is so there's a difference when you use them. You give me a solution, I spit out optimality gap statistical estimate for you and the confidence interval, okay? Versus when you use it sequentially, you might want to do this. You generate a sample of size, say, 100, but then you want to use the same 100, especially if you can warm start, right, your solution of the sample average approximation to estimate your gaps. Then you can add another 50 to it, go to 150. You can do maybe add another 50, go to 200, and so on and so forth. On the other hand, you should have either SAA or some other method that gives you a sequence of solutions. And you can find it in any way. So the sequential sampling procedure will take these sort of optimality gap estimators and their variances and will give you rules to increase the sample size, and then rules to stop sampling, that you've actually obtained a good enough solution. So, and the analysis is difficult. Why? Because here, the sample size is fixed. Give me 100 sample size, and the solution X is fixed. Give me one solution. I'll do my statistical estimation. I come up with some numbers for you. But in a sequential thing, what's going to happen? This X is probably a random X, right? Every iteration, you're going to get something different. That's number one, so it makes it a little bit more complicated. Number two, the N, when you stop and spit out a confidence interval and an optimality gap estimate, that sample size, you don't know it. It depends on what you generated so far, right? There's even more dependency going on. And when you stop, it's the number of samples you used when you stop is another random variable, right? Here, this n is fixed sample size. You can take it to limit n goes to infinity, but it's still, sample size is going to infinity deterministically. When you do this sequentially, the sample size when you stop, when you run the procedure one time, it'll be 150 samples. Next time, it'll be 300 samples. Next time, it'll be 350. That's the random variable itself. Okay? So the analysis is a little bit more complicated. But sort of the general, so some general ideas are like this. So two types of stopping rules. So one type of a stopping rule would be a little bit more general. I call it the relative width. Basically, it gets these candidate solutions at iteration k. So I'm going to generate x1, x2, x3, or x hat 1, x hat 2, x hat 3. Okay, at each iteration, I'm going to generate a gap estimate using sample size nk, all right, gap of this solution x at k, all right? And I'm going to generate a sample variance estimator. So this could be single replication procedure, two replication procedure, multiple, whatever you want to use, right? So I have an optimality gap estimator and some kind of a variance estimator. I need some properties of these, nice properties. So I want this to converge to the true optimal optimality gap, where this is also converging to a solution. And I want this to converge to the true variance, and so on and so forth. So I want nice convergence properties on this, right? Otherwise, the method might not work. So that's a basic requirement. Another thing is, if this sequence of solutions doesn't give you good solutions, what's the hope? You might not say, I found a high-quality solution. So I need also, eventually, not the beginning, but eventually, this sequence must generate good solutions. Like if you take sample average approximation, increase the sample size, right? We just talked about all the conditions that this will be an optimal solution to the problem, right? So I need things like that. So eventually, I must have good solutions for this procedure to work well. Otherwise, there's no hope. And then I need some sample size increases. So sample size must increase. Remember, everything that we have studied, if you want to show convergence and whatnot, you have to take the sample size to infinity. But of course, we're going to stop at a finite sample size, and we want to find that. But in some ways, this must increase. And if I have, let's say, a finite moment generating function, this increase is going to be of order actually lower than linear. I can go lower than linear, okay? If I have a finite moment generating function. If I have less restrictive conditions, so for example, I must have at least 2 moments, right? Because I'm estimating variances. I need finite variances. So if I have, let's say, this is the basic one you must have. So finite second moments. Then in this case, the sample sizes has to increase larger than sublinear, right? It's like log k. You must have the sample sizes increase a little bit. There are some terms there, but let's say a little bit higher than linear. 1.1, say, okay? So I mean, there are some terms there, technical, but it's a little bit higher than linear, but it's still quite low. You can still go quite low, okay? So you must have these, but these are like the lower bounds that you must increase. And then, if you have these conditions satisfied, then here's what you do. So the relative width stopping rule does this. Any questions on this? May I erase it? Okay. So the stopping rule would be T is the terminating iteration. It's the first time your gap estimate, all right, using sample size nk of the solution of the kth candidate solution, think of it something like that, is sufficiently small, and that's going to be something like this. So as a fraction of its sample variance, a sample standard deviation. Okay, that's why I call it relative width. Okay, so if there's a lot of variability in your problem, you might be willing to start with a larger gap estimate because you cannot estimate it very well. Or, I mean, inherently the problem has large variability. If you have low variability in your problem, then you stop with a smaller optimality gap estimate. Okay? You can also force this to be less than some value so that you stop when the point optimality gap estimate is, let's say, some fixed number. Okay? That's also doable. The theory works. The only problem is this thing is convergent to a particular variance value, right? We can show theoretically. And I want good estimators that will have the convergence properties. So suppose this is converging to a variance that is 100. But you're forcing it to be less than or equal to 50 to stop. Will it stop? It's converging to 100, and you just keep trying to find something that's less than or equal to 50. And I've actually done this. When I was working on this in my competitions. I'm like, why does it keep going? It keeps going, keeps going. And I'm like, oh, of course. Right? So it's sometimes better to leave it like this. Or if you know what that variability, or if you've got a good estimation, you can then use the information. But for technical reasons, there's another, like, a small term here. Let's say 10 to the minus 7. So it's for numerical stability, but that's not that important. So it basically stops when your point optimality gap estimator is sufficiently small relative to your sample standard deviation. Okay? And if you do this, and if you increase the sample sizes at least of order log n in a particular way, then you can guarantee when you stop, the solution that you find is you give a confidence interval on it, is like a GNT. You output this solution with this confidence interval. So it's a little bit different than the other confidence interval we looked at. So there's another, say, 10 to the minus 7 here, but that's not that important. So this is the confidence interval width you produce. And you can show that if you want 90% confidence interval, it's going to show up in the sample size increases at 90%. If you want higher confidence, you have to increase the sample sizes a little bit higher. Okay? If you want lower confidence, you can increase the sample sizes lower. Then you end up with this confidence, and you say, hey, I found the solution with the confidence interval this, with approximately 95% confidence. Okay? Something like that. So that's a stopping rule that uses these optimality gap estimates. And you can embed it in many methods. All right? So you can use any method you like, but independent of it, you have to, and you can have internal estimates. So one thing I've noticed people do, they generate these candidate solutions in an algorithm, and they use samples to do that. But they use the same samples to evaluate how good that solution is, which creates some kind of a bias, right? Because you use the same samples to generate your candidate solution, you use the same samples to evaluate it somehow. So it might be good to do it outside as a secondary sort of stopping rule to make sure you're finding good solutions. Okay? So this is one stopping rule. As I said, I call it the relative width. You can also do fixed width. Any questions on this? All right. So the fixed width will require those exponential rates of convergence, like that piecewise linear or finite assumption. So it's a more restrictive class of problems, because you need like a really strong exponential rates of convergence for this to work. And this is a little bit more general. But if you have this type of problems with that assumption, then you can change it like this. Use directly that confidence interval width say the single replication procedure, generate a sequence of solutions. Your gap estimator plus, let's say, S and K. Let's use the single replication procedure. And this is my confidence interval estimator, right? So I'm going to stop. Or I can do this. Something a little bit more, okay, is less than or equal to some fixed width, right? So when the confidence interval width, so how much I believe the optimality gap is less than some fixed number, then I'm going to stop. That's what I call as a fixed width stopping rule. And why this will work? Because there's always the sample size. Eventually, this will go to 0. Versus the other one, right, is looking at a fraction of the sample variance. It might not. But this will always, you can always get this epsilon satisfied at some point. Okay, with probability 1, it will stop. When it stops, you output this, right? Just the same, without this additional term type of a thing. And T of this is your candidate solution, and this is the optimality gap on it. Something like this. Okay? And you can show, yes, you have approximately, say, 90% confidence. Okay. So these are different ways you can use them, like the optimality gap estimate, which is important on its own, because all you can do is get an approximate solution. But you can also use them in a sequential fashion to determine when do you stop, like what is a good solution, and as you sequentially increase the sample size. Okay? So, any questions, comments? And that's perfect on time. So, well, thank you very much.